All right, so we are going to talk about conditional statements. We did our homework last time, and we talked about inductive reasoning and counterexample and conjectures, right? So first thing we're going to talk about is conditional statement. All it is a logical statement, and it has two parts, a hypothesis and a conclusion. And it can be made in the form of an if-then statement. So if you are reading a statement and it says if blah, 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 then blah, 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 then you know you're dealing with a conditional statement. Symbolically, we can write it with P's and Q's. So P is going to be our hypothesis, and then Q would be our conclusion part. And the way we write that symbolically is a P, then an arrow, and then a Q. And the way we pronounce that is if P, then Q. Sometimes people will say P implies Q. That's more, you're going to see that more in your college, when you get into college and start doing logic. And then later, next class, on Wednesday, we'll talk about whether the conditional statement is true. All right, so let's look at some examples. All right, so this is written in if-then form. If I study hard, then I will pass geometry. So which part is the hypothesis? If I study hard. So I study hard is the hypothesis. That would be the P part. Okay. And then the conclusion, I will pass geometry. So that would be the Q part. Okay, so that's all we're talking about. It's just a conditional statement. We have the if part, the then part, and you can identify those pieces. Yes? Good. All right, so what I want you to do is look at these three statements and see if you can write them in if-then form, and then we'll talk about them. So yeah, these are how we would write the if-then statements. Be careful to make sure that it's saying the same thing as the original. So we would not want to say if an animal has a tail, then it is a monkey. We want to say if an animal is a monkey, then it has a tail. Okay. So keep in mind that conditional statements, these can be true or false. So they don't have to be true necessarily. Like, for instance, we said that a monkey could have a freak accident and get its tail chopped off, and then that statement would not be true, right? I know, we're so gruesome. All right, so in order for it to be true, it has to be true every time. In order to show that something is false, then we only have to provide one counterexample, and that monkey getting its tail chopped off, that would be a counterexample. All right, so that's kind of what we said earlier. You good? Can I move on? Okay, the negation is a new thing. I need you to write that down. The negation of a statement is the opposite of the original statement. So think of negation, the word negation, as the negative. All right? This kind of sounds like negative, right? Negation, negative. It's the opposite. So for example, if I say the ball is red, then the negation of that is the ball is not red. Be careful though. It is not okay to say the ball is blue. That is not a negation, right? That's very different than saying the ball is not red. The ball is not red can mean it's any other color besides red. Also be careful of if my original statement already has a not in it. Jedi Masters do not use lightsabers. So the negation of that would be Jedi Masters do not? No. We would say they do use lightsabers, right? So just be aware of that. All right, moving on. So I'm going to have 4 more kinds of statements on this slide, and we're going to use this original one. So my original conditional statement is, if Mrs. McCahan is my teacher, then I go to P&H. Okay, and let's assume that I'm the only Mrs. McCahan out there. Okay, that there's no other Miss McCahan teaching any other place else. And let's also assume that I don't teach anywhere else, because I don't. Like I don't teach, I don't know, at college or something. Okay, so for this particular conditional statement, that's true. Yes? Okay. So the converse, this happens when we switch the hypothesis and the conclusion. So when I write the converse of that statement, I'm going to say if, what would come first? I switch the hypothesis and the conclusion, what would come first? If I go to PNH, then Mrs. McKayan is my teacher. Okay, that would be the converse. Is that true? If I go to PNH? So give me a counterexample, and that would prove it false. So yeah, anyone who goes to PNH and does not have me, that would be a counterexample to show that that's false. Okay? So this converse in this situation happens to be false. All right? Conditional statements and converse statements, they can be true or false. It depends on what the statement is. Okay? Next one, an inverse. An inverse is when we negate the hypothesis and the conclusion of the conditional statement. All right, so go back to the original, the conditional statement. What did we say negate means? Yeah, we make it negative, we make it opposite. So I would say if Mrs. McKayan is not my teacher, then I do not go to PNH. Is that true? So can you think of a person that doesn't have me as a teacher but still goes here? Yeah, that would be a counterexample. Okay. Yeah. All right, so the next one, contrapositive. Contrapositive. All right. Does not want to work. All right, there we go. Contrapositive, that's when we negate the hypothesis and conclusion of the converse. What was the converse again? What does it mean to do a converse? To switch, right? All right, so I'm going to negate the switch. So I'm doing both, right? Bless you. So review. Converse means to switch. Inverse means to negate. Contrapositive means to do both of them. Negate and switch. Okay? So here's how that would look. If I do not go to PNH, then Mrs. McKayan is not my teacher. What do we think about that one? Is that true? Yeah. Yeah, if you don't go here, then you can't have me as a teacher, right? There's no way. Yeah, so contrapositive and the original conditional are the only ones that ended up being true. The converse and the inverse were both false. Yeah, so notice that each of these can be either true or false. It doesn't matter. It just depends on the actual statements that you have. Okay, and next time when we do truth tables, we'll get into more of how do we know whether it's true or false. Okay, can I move on? All right, equivalent statements. Please don't write all of this. I want you to focus on the word equivalent. What does equivalent mean? Equal. So equal statements means they have the same truth value. Okay, so they either are both true or they're both false. So for example, We had two statements on the previous slide that were both true. Which ones were they? Yes. Good. The original conditional and the contrapositive are both true. So that means those are equivalent statements. All right. We also had two that were false, right? Which two were false? Which two on the previous slide were false? Yes. Good. The converse and the inverse. So since those were both false, those are also equivalent statements. Okay? So that's all that means, is that they have this, they're either both true or they're both false. That's what equivalent means. Okay? Any questions about that? So yeah, don't feel like you have to write all of those words. All right. Now, another kind of statement is a biconditional statement. There's the bell. All right, so this is going to contain the phrase, if and only if. That's how you know you've got a biconditional statement if you see that phrase, if and only if. And the reason we write that is because we're essentially writing the conditional statement and its converse. That's what a biconditional means. So if you use that prefix bi, what does bi mean? Two. So I've got two statements in one, essentially. I've got the conditional and its converse all in one statement. Okay. So you can only write a biconditional statement when the statement and its converse are both true or both false. Okay. Otherwise, that biconditional statement doesn't make sense. And then here are the symbols. Again, if I'm using P and Q, remember P is my hypothesis and Q is my conclusion. Okay, notice that I have the double arrow there. That's how I would write that. That shows that I'm doing if P then Q, and also if Q then P. It shows that I'm covering both statements. Also, this right here, the IFF, that's very common to see. So that doesn't mean someone misspelled the word if. It just means if and only if. All right, so here's an example. All right, we have this biconditional statement in yellow here. An angle is a straight angle if and only if. So I know it's biconditional because of this phrase. Its measure is 180 degrees. Notice that the sentence does not start with if. Do you see that? All the other ones started with if, don't they? So a biconditional statement doesn't have the if in the beginning. It has the if and only if in the middle, between the hypothesis and the conclusion. So this is like my P, and this is my Q. Okay. So if I want to split this into the two different statements that it represents, then I can say the conditional statement. So if P, then Q. So that would be, if an angle is a straight angle, that's the P part, then I would have the Q part, right? Then its measure is 180. That's one thing that says. What would the opposite look like? What would the converse look like? Yeah. Good. So the converse just means we switch. So if Q, then P. All right, so if the measuring angle is 180, then the angle is a straight angle. So that one statement in yellow represents both of those things, which is why we write it, because it's easier and quicker. All right, so let's look at an example. All right, so we're going to consider this statement. X equals 2 if and only if 3x plus 5x equals 10x minus 2x. First of all, is this a biconditional statement? Yes, how'd you know? If and only if. So now we need to figure out, is this true? So we need to see, does it work both ways, right? So if this is my P, right, and this is my Q. So if P then Q, what do I do to test if P then Q is true? Yeah. Yeah, I'm going to plug in 2 into all the X's and see if that works. So I'm going to do this. All right, so I'm going to have 6 plus 10 equals 20 minus 4. So I'm getting 16 equals 16, and that's true, right? So if P then Q is true, so now we got to do the converse, right? So if Q, then P. So what does that mean I got to do? I've got to start with the equation, right? And then I need to solve it. All right, so let's solve. Combine like terms, 8x equals 8x. And what do I do to solve? X's are on both sides, so we need to subtract to get the x's on one side, don't we? All right, so I have to do minus 8x, and what happens? Cancels out on both sides. What does that mean? Yeah, what does 0 equals 0 mean? Infinite solutions, right? So that is true, and that's why we would say back in Algebra 1, infinite solutions. So what does that mean, infinite solutions? Say again. X could equal any number. So it could equal 2, but it could equal a lot of other things as well. So is this part true? No. No. So this is not a true biconditional statement, okay, because of that infinite solutions. So we would say no on this part. All right, so here's our next statement. 2 segments are congruent if and only if they have the same length. Is this a biconditional? Yes. Why? Because of if and only if. All right, so now we need to figure out if it's true or false. All right, so here's my P. 2 segments are congruent. And then here's my Q. They have the same length. So if P, then Q. So if 2 segments are congruent, then they have the same length. Is that true? Yep. So that one's true. Now I'm going to do the opposite, the converse. If Q, then P. So if 2 segments have the same length, then they are congruent. Yes, that is true as well. So that is a true biconditional statement. So this is like back when we were doing the parallel lines and and they do not intersect. Remember how we said we could say it either way? That's because that's a biconditional statement. That could be written as a true biconditional statement. So that's why it worked on that one, whereas maybe the monkeys one, we could not write it that way, right? We could not write it as a biconditional because it wasn't true both ways. All right, so that's what biconditional is. Any questions on that? Moving on. All right, perpendicular lines. We have 2 perpendicular lines, then they form, if they form to intersect a right angle. Okay, so decide whether the statement about the diagram is true, and we're going to explain our answers using the definitions that we've learned. Okay, so their first one is saying KLJ, that's this one, and KJL are complementary. So what do we think about those? Are those complementary? Yeah? Yes, because 54 plus 36 equals 90 degrees, and that's what complementary means, right? Okay, cool. And then KL and LJ are perpendicular. KL is this line, and LJ is this line. Are those perpendicular? No, why not? They do not form a right angle, right? Okay, and then next one, MKJ is a right angle. MKJ, that's that one right there. What do you think about that one? Is that a right angle? Why do you say yes? Okay, well, that box wasn't originally there. I drew that in there. Why is that true that that's 90? Ah, it's vertical with the one that they already drew in, isn't it? Okay, and vertical angles are equal. So we're going to say yes, because vertical angles are equal. I'll say congruent instead of equal. All right, KJL is an acute angle. KJL. That's this double arc, right? Is that an acute angle? Yes, why? Yes, it's less than 90 degrees. All right, and then point N is in the interior of KLJ. KLJ, that's the blue outline. Is N in the interior? No, why not? Where is it? It's in the exterior. Okay, so all of those were based on definitions that we had done. And all those definitions can be written as biconditional and if-then statements. All right, let's make sure we're good on symbolic notation, because as I said, on Wednesday we're going to do some truth tables and it will be all kinds of P's and Q's. All right, so conditional statement, if P then Q, can be written as, remember we have P, then the arrow, and then Q. And that's pronounced if P then Q. Right, we already knew that. So the second one, the converse, can be written, that's going to be what? Converse is when we do what with the hypothesis and the conclusion? Switch. So that's going to be if Q, then P. So that's Q arrow P. And then inverse. What did we say we do on inverse? We negate. So that symbol you guys haven't seen yet. The way we show negate in these logic symbols is I use a little squiggle. So I'm going to negate the original conditional. So I'm going to use squiggle P, then an arrow, and then a squiggle Q. So I negated both the hypothesis and the conclusion. Okay, so that's how you do a not. So that can be read as if not P, then not Q. And that's how you would read that. And then contrapositive, what do we do for contrapositive? What do we say that does? Negates. Yes, negates the converse. So we flip and negate, right? So I'm going to take that green one and put little squiggles in front of it. So squiggle Q, arrow, squiggle P. And that's read, if not Q, then not P. And then biconditional, how did we say that goes? If and only if. So, and the way that looks symbolically is I'm going to have a double arrow, right? So the way that's read is P if and only if Q. It has that double arrow. Okay, so remember those symbols. You might want to have that out next time when we start doing truth tables, so don't lose your notes. Moving on. So remember, we talked about inductive reasoning in our homework. So can someone remind me what inductive reasoning is? Inductive reasoning. So since inductive reasoning is based on patterns, you've done it a lot in Algebra 1 with finding patterns in tables and things like that. And you can use, you've used it in life maybe. So you might say, I noticed that my grandma always goes to the bathroom right after we eat lunch or something. So whenever you eat lunch with her, you'll be like, oh, she's going to go to the bathroom. So that's inductive reasoning, right? So deductive reasoning is different. It's not based on observed patterns. It's based on facts and definitions and logic. All right. So for example, if our lunch lady says, the school calendar states that the pizza is always going to be served on Mondays. And since today is Monday, and it actually is Monday today, we would conclude that they're going to serve pizza, right? Because this is a rule. Think of deductive reasoning. These are all rules. Rules that someone made, right? Either with a definition or a fact or logic, rules of logic. So if our lunch lady says, okay, the rule is on Mondays I serve pizza, then you know, okay, if it's Monday, I'm going to have pizza. or that it's going to be down there at least, right? So that's what deductive reasoning is. Okay, and how does this differ from inductive reasoning? So inductive reasoning, that same example, all right, that would have been like, let's say the lunch lady did not make that rule. Maybe it's not posted on the calendar. But you've noticed the last 3 Mondays that they serve pizza for lunch. So now that it's Monday again, you might say, they probably have pizza, right? That would be inductive. Deductive is when they say, no, we have pizza on Mondays, and that's the rule. Okay? That's the difference between inductive versus deductive. Any questions on that? Yeah. Okay, so I want you to look at both of these examples. One of them is inductive and one of them is deductive. So I want you to figure out which one you think is inductive, which one is deductive. Yeah, so this one can be a little bit tricky because it's just that the ones that he knows of, but that's what makes that inductive. Versus deductive, these are the facts, and we can't dispute them, no matter who is looking at brand Y or brand X. Okay. All right, so since deductive reasoning is a little bit stronger, right? It's based on fact. We have a little. We're going to have more solid conclusions. All right, so the law of detachment is something that we use in deductive reasoning. And notice what we have to have when we first start. If we have a true conditional statement, so we have to have a true conditional statement, and we have to have a hypothesis that happens. Okay, so I have to have something like P, if P then Q, and it has to be a true if P then Q. And I have to have P happens, right? If I have both of those conditions, then I can conclude, then I know that the conclusion must happen. So Q has to happen, must happen. So let's come up with an example. All right, let's do something that we can't argue with. Let's say, all right, here's my conditional. If it is Monday, then it is a weekday. Would you agree with that? Can't really argue with that, right? That's true. Yes? Okay. So, if I have this true conditional statement, this is true, we all agreed that it was true, and today is Monday, so we have P happening right now, right? So today is Monday. What can I conclude then? Today is a weekday. That would be my conclusion. It has to be true, right? So now look at this next part. It says, what can we conclude if we are given a true conditional statement and the conclusion happens? So we'll stick with this same statement, right? So here's our true statement. But what if I said, instead of it is Monday, what if I said, okay, it's a weekday? Would you know anything? It could be Monday or it could be some other weekday, couldn't it? Okay, so we can't make a good conclusion, can we? All right, so it might be Monday, that might be true, but it may not be. All right, so we don't want to make, in deductive reasoning, we don't want to assume anything, right? So that would not be a valid conclusion in deductive reasoning. Okay, so we would say no. If we know the conclusion is happening, that does not necessarily mean the hypothesis is happening. Okay, so let's look at some more examples like that. All right, so in this first one, we're going to state a valid conclusion if we can. All right, so they're telling us that these statements are true. So these conditionals are true. If Jana works this weekend, then she can buy an iPod. They're saying that's always true. All right, and then they said Jana worked this weekend. So what is our conclusion? So yeah, she worked this weekend, so that means she can buy an iPod. So Jana can buy an iPod. All right. Then let's look at this next one. If TJ's car breaks down, then he will be late for his job interview. Okay, that's a true statement. So then here's what happened. TJ was late for his job interview. Can we make a conclusion? No. Can we say that his car broke down? No. It could have, right? It might have been the reason he was late for his interview, but it might have been some other reason, right? He could have overslept and missed, not heard his alarm, and that's why he was late. So I can't conclude anything. There's no valid conclusion here under deductive reasoning. Are we okay with that? We understand the difference? Okay. So that's the law of detachment. We also have the law of syllogism. Write that one down. Syllogism. So notice in this one, I have to have two conditional statements that are true. And notice that the two conditional statements, that the conclusion in the first one is the hypothesis in the second one. Do you see that? The Q is repeated. That's important. So if I know that, then I know this, I can write this conditional statement, and that it's true. If P, then R. So it's like I take the bookends. The middle is the same, and I can take the bookends and make that into a true conditional statement. R is another statement. So I'll show you this example. Okay. So in this example, notice that Casey goes to a music store. That's not a conditional statement, is it? It doesn't start with if. So that's not our conditional statement that we're talking about. It's down here. So if Casey goes to a music store, that's like my P, right? That's the hypothesis of the first conditional statement. She shops for a CD. That's my Q. All right. So in the next statement, it starts with if Casey shops for a CD. That's the same as this green one right here, right? So this is a Q again. And then now I have a completely different thing. Then Casey will buy a CD. So this is my R. So you see how I have three different types of statements. Okay? So this is if P then Q. This is if Q then R. Question? Yes. So now, if I continue with this law of syllogism, then I know if P then R. So what is that going to look like? What is if P then R going to say? It'll say if Casey goes to a music store, then what? She will buy a CD. Then she will buy a CD. Okay? That's our conclusion. We know that has to be true. If those original two are true. Now, they're telling us this is true. I know this seems really odd, and we probably don't know people that are this compulsive, right? But this is Casey. She always does this. Anytime she goes to a music store, she shops. And anytime she shops, she buys. Okay? All right, so then we know if she goes into a music store, she will be buying. Okay? So, going back to this original question, it says, Casey goes to a music store. Given these statements, can you conclude that she's going to buy? Yeah, because now we have this true conditional statement, and we have the hypothesis happening, right? So we know that conclusion must happen. So this is a combination of both law of detachment and law of syllogism. Okay? So those are two laws in deductive reasoning that I need you to know. All right, so look at this one. This will be our last problem. Look at this one and see if you can put them in a logical order. Yeah, by underlining them and color coding them, we can see that 2 has to come first. It starts with red, then goes to blue, and then 1 goes blue to green. And then I got to go from green, that's number 4, 4 to black, and then black to the double red. This number 3, those are negations. Those don't appear again anywhere, right? So using the law of syllogism, I can write it in 2, 1, 4, 5, but I can't use number 3. Okay?